So far, we only talked about, a system in which we had two different coins, 1 penny and 1 quarter. But we could generalize this sort of analysis for systems in which we had, many different type of coins, much larger than 2. Okay? So what we could do is we could consider, a more general case where we just have n number of different coins and what we wanted to calculate was the multiplicity of k number of heads being face up for this collection of coins. So k is number of heads up. All right, and so the general formula that we would use to calculate the multiplicity, where it's sort of abbreviated like this, it would be this formula, where in the numerator we would have n factorial divided by k factorial times the factorial of n minus k. All right? And so this may seem like a strange formula, but it's actually a formula that shows up in a lot of different branches. Okay? And so another way that you'll see this formula abbreviated would be like this. And this formula, or at least this sort of ratio, this is known as the binomial coefficient. And this would be for the case where n is greater than or equal to k, and where both of those are greater than or equal to 0. Okay? So mathematically, this is what this sort of analysis simplifies down to. The way you could at least think of it is this formula would be for the case where you want to choose k elements from some group of n objects. Okay? Right, and so in our case, we want to choose, the case where we have k number of heads up from n number of coins. All right, and so that's why this sort of equation is appropriate for the analysis that we want to do. This is something that you may have seen or will probably see in your stats class. Okay, in any case, so this is sort of the general formula that one would use if you wanted to figure out the multiplicity of a macrostate where k number of heads were up for n different coins. All right, so let's start plugging in some numbers to get a feel for what this equation would predict for us. Okay. All right, and so let's consider the case where we have, 100 coins. Okay. In this case, the total multiplicity of our collection of coins would be 2 raised to the 100. All right, so that's a large number. Okay. In any case, what we could do is we could calculate the multiplicity of kind of various different cases of having k number of heads up. So let's consider the case where k is equal to 50. So in our collection of 100 coins, what is the number of different ways that we could get 50 coins to be face up? Okay. And so what we do is we take n, so that's 100. So 100 factorial divided by k factorial, so 50 factorial. And then also in the denominator, we have n minus k. So 100 minus 50 factorial. Okay? All right, and so if we actually go out and calculate this number, what you get is 1 times 10 to the 29th. All right, so there's that many different ways to have, or that many different microstates in which 50 of the coins would be face up. All right, so that's a very large number. All right, we could compare this to the multiplicity of the case where we have no heads up. So every coin, somehow after we flip them, we're face down. And so in this case, once again, we have 100 factorial in the numerator. Our k is 0 factorial, and if you remember from, I guess, any of your calculus classes, 0 factorial is just 1. And then n minus k would also be just 100 factorial. Okay? All right, and so essentially what we're doing here is taking 100 factorial divided by 100 factorial. And so what we get there is 1. There's literally only one way to get 100 coins face down in our collection of 100 coins. Okay? All right, and so we have the multiplicities. And so what we can calculate now is just the probabilities. Okay? So what's the probability that we can get if we flipped 100 coins, what's the probability that we would have 50 of them, exactly 50 of them, face up heads? All right, and so what we do is just 1 e to the 29th divided by 2 raised to the 100. And if you have a calculator that can do this calculation, the number that you get is 0.08. So there's only an 8% chance that you would get 50 coins to be heads up. All right? But, that's much smaller than the 50% we saw when we only had 2 coins, right? But if we compare this to the probabilities of other results, so what's the probability that we would get, all the coins face down, tails up? So that would be 1 divided by 2 to the 100. The number you get there is about 10 or 8 times 10 to the negative 31, right? So that's a really low number. And equivalently, if you did this calculation for the case where you got all the coins to be face up, heads up, you would get the same number. Okay? All right? And so the probability that you would get 50 coins face up, even though it's a small probability, it's still order of magnitudes more likely to happen than getting all your coins face down or all your coins face up. Okay? Right? And so we could compare that to the case where, we only had 2 coins, right? And the probability of half of them being heads up was 50%. And that distribution was a little bit flatter, right? Because the ends of the distribution to get either 2 coins face up or 0 coins face up, those probabilities were 25%. If we can compare that to here, though, we see that, the probability of getting half of the coins face up is way more likely than getting 0 or all of them face up, right? And so that's generally true. At least the observation that you should see here is that if you increase the number of coins in this collection and you flip them, right, essentially the distribution of how many coins you get face up, that distribution gets narrower. And so to visualize this, what we could do is we could take a look and we could compare, the distribution of omega k for the case where we have 100 coins. We could compare that to the distribution of omega k to the case where we have 10,000 coins, right? And so for the case of 100 coins, we see that our distribution looks like this, and the width of the distribution is that, right? That would be essentially the standard deviation of that distribution. And so if we plot it where, 0 to 100, we see that essentially at the wings of the distribution, it's really rare. And then we have this sort of normal distribution here in the middle. If we increase our number of coins, though, to 10,000, and we still plot the minimum and the maximum k values here, we see that our distribution is much narrower. In fact, it's almost a line there. Okay? Right? And really, the only macrostate that you would observe, right, that has like a reasonable probability of being observed, is the one that's right in the middle. Okay? And so, at least what I want you to get out from this is that the distribution of our multiplicity, omega k, that with the standard deviation, it decreases as the number of coins in our collection goes to infinity. And so what ends up happening is that at this limit, really the only macrostate that has a reasonable probability is the one that's observed. Right. Okay? And so, I kind of went through this example with coins. But this sort of case, where we're looking at how the system behaves at the limit where our system, the number of objects in our system is infinity, that's known as the thermodynamic limit. Okay? And so, generally, just to reiterate, when we approach n goes to infinity, that's known as the thermodynamic limit, and at n approaches infinity, we only really observe a macrostate that's the maximum.